Okay, gang, this is a continuation of our video from earlier. When we left off, we were discussing distributions, and we were discussing a control group distribution with an experimental group distribution. And we noted that for this population, 64 students, we had a value of 1.64 on a z-score. If you remember from last week, what are z-scores? Z-scores are calculated by taking the mean of a population, assuming that that population scores are distributed in a bell curve, Gaussian curve, normal distribution. And we know, based on statistical probabilities, that a lot of phenomenon in psychology, in humanity, exist in a bell-shaped type curve. And so we can make some assumptions based on this. And so we know that a score of with a standard deviation of 6, a score of 206 would put about 34% of the population in between the mean and the first standard deviation. Interestingly enough, a score of 1.64 is significant for a lot of statistical procedures that involve z-scores, that involve populations. And what I've done is I've shared some information with you that helps explain that. So if you go now to our class module and you scroll down to the z-score table, what this is it's actually taken from this textbook that helped me understand stats. And what it does is it describes the percent of a population that is present in relation to different z-scores. So, for instance, if we have a z-score, let's just take a z-score of 1. So a z-score of 1, looking at our example, in this case, let me stop sharing so you can actually see it. In this case, a z-score of 1 is 206. So that z-score table that I shared with you is basically saying exactly what I said. 34% of the population of this whole, it's basically like somebody took a pie chart, cracked open, as like an egg, you're able to crack open a pie chart and then laid it out flat like this. So most of the egg, most of the content is like right here. And some of the egg is like spilling out, like 5%, like 5% of the egg spilling out down there, 5% of the egg spilling out down there. So, most of the egg is right here. So 34% of this cracked open egg, this cracked open distribution pie chart is right there. And that is what this chart here, this z-score table, is telling you the percent of scores from z to the mean. So 1 is 34% roughly. Now, when we are talking about statistics and we're talking about levels of significance, there are typically 3 levels of significance that we look at. And it depends on the type of assessment. It depends on the type of experiment that we're doing as to what our alpha level is, or our level where we're going to consider, hey, this has less than a 5% chance of just occurring by a random chance. And so the z-score table actually gives you a 95% chance. And that occurs at roughly 1.64. So the score 1.64 is telling you that roughly 50%, or excuse me, 45% of that distribution is between the mean and the z-score of 1.64. So 1.64 standard deviations above the mean, you'd expect to find 45%. The other 50%, so then now you do a little bit of math in your head. The other 50%, like why are you at 45%? So now what it's showing you is this distribution right here. 45% of scores lie between the mean and 1.64. There's another 50% of scores because, again, this is symmetrical with a normal distribution. There are another 50% of scores down here. So 50 plus 45 equals 95%. 95% of the distribution is here. Another 5% is out in the upper tail. That is a one-tailed test. And so we can also make this a little bit more precise. If we do a two-tailed test, we would want to have 2.5% in the because we'd want to then look at both sides. We don't know whether things could get better or worse. So if we don't know, we don't have a clue with our hypothesis, we're like, we just want to look for a significant difference. We often run a two-tailed test. Things could get better with the instructions for the fifth grader, or they could get worse. In this case, they had a pretty strong hypothesis that things were going to get better. And we'll talk about whether they did or not in just a minute, statistically speaking. So if I'm looking for 2.5%, I want 47.5. So then my z-score is almost 2. My z-score is almost 2. So it's basically 2 standard deviations, leaves me, and it's 1.96. 2 standard deviations leaves me roughly right at 2 is about 2%, 2.3%, 2.28% in either tail. The statistically significant number for us running our stats, we look for a z-score above or either above or below. So we could also have negative z-scores, remember, above or below 1.96. So same thing if we're doing a two-tailed test. If we're doing a one-tailed test but looking below, we'd use a negative 1.64 because it's assumed that the distribution is symmetrical. It's a perfect bell shape. Friends, that is a z-score distribution. And it helps you understand the next step. The next step is what we normally deal with in statistics. So a z-score, something very well established. Thousands upon thousands of people take it, like something like an IQ test, something like a Stanford-Binet or a Wechsler, something that just, we have so much data. Yes, we've collected so much data. And yes, the population does exist in a bell curve. It's very well established. That's not oftentimes the case when we're dealing with new data, new information, new constructs, or modified constructs. And so, for instance, if we were dealing with a depression scale, we wanted to come out with an assessment for depression. Many of us that are going into counseling would like to know clinically, based on our observation, whether somebody's depressed or not, but also might want to rely on a scale like the PHQ-9, the Beck's Depression Inventory, the BDI. And so we want to then examine, like, is this valid? Is one score then is one score if somebody scores really really high on a Beck's depression scale, now take those numbers away from the fifth graders, but somebody scores really really high, are they really depressed? And so there's a lot of data that say that there's a small chance that if they had a really high score, again, you have confidence intervals on whether or not that, and you also have you want to take in consideration possible error. So what happens is when you get into t-distributions or samples, something that's really not, we're really getting to try to look at the population, but we're going to take a segment of the population. That then takes away the z-scores and it introduces something called t-scores. And t-scores are built on the same premise. T-scores are built on the same premise that, and that those can be found down here, that most things exist in a bell curve or a normal distribution, but it also takes into consideration that we don't know for sure, and we might have some sampling error, and we don't have the population. So for instance, let me try to illustrate this as best I can from memory. This is a whiteboard share. Oh, is it going to go over here? Is it going to go over here? It says it's loading my whiteboard. Let's try this one, a new whiteboard. Okay. So let's see how close I can get to drawing a bell curve. So this is me trying to do my best to draw a perfect bell curve. It's not the best. It kind of looks like a ghost. It could draw some eyes, and it's Halloween. But let's say I did draw this perfectly into a bell curve. So this would be then a z distribution. Z dist. If you're going to look at a t distribution, and so this would be a population. A t distribution looks at a sample, and samples have more error because you don't know. It's like these polls for president or whatever. You don't know whether you're actually sampling the people that are going to vote. You think you will. And so what a t distribution assumes is that it's going to look quite a bit like a z distribution, except there's going to be more room in the tails and the peak is not going to be quite as high. The mean might be spread out a little bit more. And so the mean might be here, but you're also giving more room for standard deviations. So standard deviations are very tight. They occur at z-score of 1.64. They have score of a z-score at 1.96. So these are very, very tightly distributed here. The t-sample distribution is a little bit flatter. In other words, the scores are a little bit, it may not have it may not have as many clustered around the mean exactly. It may be spread out a little bit more. So it gives you more margin for error, because again, you don't know that you're exactly representing the population. That's what a t-sample distribution is. Let me see if I can go back to sharing my the t-score table. So the t-score table then looks like this. Here's cutoff scores for the d distribution. It does a better job, I think, of clearly denoting, okay, well, I'm giving myself a 10% chance of a type 1 error. Now I'm giving myself a 5% chance. Now I'm giving myself a 1 in 100% chance. Here's a one-tailed test. Here's a two-tailed test. So what will happen is when you run a t-test, you get a t-score, a t-value. And basically that t-value that you get is what I just showed you. It's like a z-score, only it's giving you a t-score of where this difference lies among the distribution of scores. And so if we want a 0.05 cutoff, and degrees of freedom is related to your variables, which in a t-test is two levels of independent variable, because you're only comparing one variable with another. So you subtract 1 from your total population. And you can see the higher your sample size, if you have a sample size of 1, you have horrible, or a sample size of 2, you need some really, really high scores to say there was significance or not. And so it's assuming that distribution is basically flat. I would say if you're conducting an experiment with 2 people, don't run a t-test. A good rule of thumb is 30 is where you start to get, or 29 or 30 degrees of freedom, where you're assuming you have about 30 participants, where you can start to get close to that 1.64 number. Do you remember? The 1.64 number, if you remember from a population, was what? That was like a one-tailed test. That was the significance. At 1.64, again, that's 95% of the population is below, and 5% of the population is above. Again, I'll show you that once more. So again, you have that line there that represents the z-score of 1.64. Now, visualize this as a sample, and so the peak is lower. This is spread out more, and so you need a higher t-score because you have more margin for error. You have more error, and so you need to create for yourself more margin for error. And therefore, once you get to infinity samples, the best you can do in a t-distribution is 1.645. If you get to a sample of around 100, that's pretty good. Now your t-score, you're with 1.66, and t is very close to z. Again, this t-score is very close to what z is doing, but it's telling you that if you get a t-score with 100 participants of 1.66, you can safely say that 95 people in that sample of 100, 95 people are below that score of 1.66. Pretty crazy, right? So that's a t-score, and you can see that we've got one-tailed, two-tailed tests. And pretty exciting. I hope that made some sense to you, because then when you start interpreting t-tests, you start to, well, here's another sample from my book. So now you have, it says you have 80 cases, a fictional study of employees receiving a health promotion program. So this is still z-scores, but you could substitute t to a degree. Z-scores and raw scores are shown on both distributions, corresponding to the significance cutoff of lower distribution, cutoff based on 0.05 one-tailed. All right, so again, they look like they had some pretty big results here, because the mean, now the mean in this test went from 58 all the way up to 63. And you can see based on that sampling, the power is pretty significant. You're saying that, oh my gosh, this distribution, you have roughly about 90% of the population that's now above the mean because of whatever condition that you put them through on this experiment. T-tests work much the same way. So when you're visualizing this, visualize that z-score now, but with t-tests, it's, again, depends on the size of your sample, but it's still based on that premise of a normal distribution. Again, I hope that there's a light bulb flickering. I'm trying to do this my best broad brush without getting too formulaic and getting into really detailed and idiosyncratic descriptions. I want to make this to where you're at least able to decipher when you're looking at stats what it is that you're looking at. So hopefully those tables are making sense. Here's the null hypotheses. So basically, here's a two-tailed test, and if you have if you have a score or you have a distribution, that falls somewhere in between this, a critical value of negative or positive, you're going to fail to reject the null hypothesis. If you have this critical value, this looks like a 10% chance. This looks like we're giving ourselves just a 10% chance of making a type 1 error versus being more stringent. if you have scores that or average, means that that fall out here in the tails, then you want to reject the null. So the null hypothesis is stated as the negative. So if you're trying to say, as our example began, if you're trying to say that this test prep for fifth graders, your hypothesis, yeah, it's going to help fifth graders test score, then you want to state it in the negative. And so if you're interpreting this formula, again, I'm trying not to get formulated, but sometimes you have to because it's how you read it. The null hypothesis is stated as H0, hypothesis 0. Then the mean for the experimental group, or the mean of the control group, will equal the mean of the experimental group, which is giving you, again, the probability that, yeah, there is no true difference. The null hypothesis here is the mean, and a right-tailed test is less than or equal to the experimental group. In this one, the left-tailed test, the null hypothesis states that the mean is greater than or equal to the experimental group. Sorry. And then your alternative hypothesis. Sorry, my brain's getting ahead of me. Your alternative hypothesis is your true hypothesis. So your alternative hypothesis states that the means are not equal, or one mean is bigger than the other, or one mean is less than the other. And so this would be a two-tailed test, and this would be a one-tailed test, and you have to specify which side of the distribution you're hedging your bet on, you're betting toward. So null hypothesis is always, you're stating it in the negative. And so if you reject the null hypothesis, yes, that's a double negative, and that's a good thing because that means that your experiment, you found significance. That's our next step. That's enough for this week. Good luck digesting that. Reach out if you have questions. I hope to hear from you next week, because I hope I described that in enough detail for you to just hopefully grasp it well enough.